Okay, we'll get started now. So this morning we looked at hardware and software already on ARCHER2, some of the places where you may want to configure the hardware or your application's use of your hardware to get best performance, and how to install your own software onto ARCHER2 if required. Now we're going to look at two separate examples of how you would use software such as data scientists would commonly use on ARCHER2, with the caveat that, as was pointed out this morning, that actually Python and R, as they come as standard, I'm not sure standardly is a word, as they come as standard, will just work on ARCHER2. Okay, you may need to install new packages that may require some configuration and a bit of work, but Python as it comes, Python already has NumPy, SciPy, some of these things built into it on ARCHER2 for you, and R with a range of packages already comes and will just run as it would on your local system. So what we're going to focus on this afternoon is actually how do you use these in a more parallel manner. How do we exploit all the cores, all the nodes on ARCHER2 using Python or R, and what are the approaches to doing that? Now, there's another caveat that I'll drop in here, which is that there are lots of different ways of doing parallel Python. There's lots of different ways of doing parallel R. We're not covering them all. And I'm not particularly saying the ones we are covering are best. They're just commonly used ways of exploiting multiple cores inside a node or multiple nodes in a system with Python or R. And so that's what we're looking at doing here. And this is sort of along the lines of, okay, you're a data scientist, you've got a program that wants to run but takes too long. You've got to process through large amounts of data. You need to use all those cores or nodes in some way. How do we how do we do that? Now, one of the ways, as we've already seen this morning, is to use job arrays or run multiple jobs inside the same job script, so you can take up and run what we would call task farms or embarrassingly parallel runs of individual applications, but on different input data sets. And if that's all you need to do, then you don't need to come in and particularly have a look at things like parallel Python and parallel R. We can just use the slow and batch system and a little bit of scripting around that to run large numbers of single core jobs at the same time. Now, you could easily argue that ARCHER2 is not a brilliant system to use for running large numbers of single core jobs, because at some level you're not making best use of that fast high performance network, which costs a lot of money and is provided to connect together the nodes efficiently. But nevertheless, if you've got very large numbers of jobs to get through, then ARCHER2 is still quite a good target for that kind of thing. And of course, it has the high performance file systems as well. So, if your bottleneck is file I/O, reading and writing files, then one of the places you can get better performance is by coming to a system like ARCHER2. So, whilst ARCHER2 is really focused on large-scale computational simulation applications, this doesn't preclude it being used for large-scale data science, data analytics work. But there will often come up situations where running a single application on a single process to do your work is just not going to cut it, because even though you can run lots of different ones on lots of different input data sets or parameters at once, your individual runs are going to take too long. And then you're going to have to parallelize somehow. And what we're looking at here is what other ways we can parallelize using Python and using R. And so in the first instance, we're looking at Python. Now, excuse me a second. Yeah, you've got to love what's the word I'm looking for? I want to say junk callers, but it's not the right word, is it? Anyway, that was nonsense. Let's get back to where we were. Okay, so not that one. I don't want that one. I want slightly getting ahead of myself. This one. So what we haven't really spoken about here particularly is the kinds of parallelism we can see, and this goes beyond this course, right? If you're really interested in parallel programming and parallelization, we do other dedicated courses to these topics, and there's a lot of detail to get into. But broadly speaking, we can look at parallelization in two forms, at least from a hardware perspective. We can look at what's called shared memory parallelism and distributed memory parallelism. Shared memory parallelism generally uses workers that are called threads, and these are individual workers from a single program that's running. Okay, and this kind of parallelism is pretty easy to implement, but you can only ever use up to a single node. So on ARCHER2, that would be up to 128 cores or 256 threads. And in reality, actually, most shared memory parallelism implementations don't perform very well up to that large number of threads, just because of the way the memory's configured and some of the complexities of the hardware. So generally, you're looking up to about 64 cores for reasonable performance. So it's easy to program, but it's small-scale parallelism. Distributed memory parallelism is one of the main ways of implementing that I've mentioned a few times, called Mpi Communication Library. Basically, distributed memory parallelism lets you send messages between individual workers. All those workers are separate running processes, so separate versions of the program, and then they communicate with these messages backwards and forwards. And because they're sending messages to communicate, they're not creating their own little workers. You can actually run all the workers here on different compute nodes and use the network to communicate data in between them. So that means you can parallelize not just inside a single node, which you can do, but you can parallelize up to all 5,860 nodes on Archer and all 750,000 cores with the same programming approach. So distributed memory parallelism is more functional from that perspective, has the potential to scale further to larger numbers of hardware resources, but it's also harder to program and more complex to do because you can't share anything between the workers. For the shared memory parallelism, you can share because one main worker creates a bunch of sub-workers called threads. They can all share the same data easily. In distributed memory parallelism, like MPI, you actually create lots of separate individual workers, and then they can only share things between them by sending messages. And so you have to physically program that message sending, and that's why it's harder to do. Okay, so with that in mind, Python has a number of built-in options for parallelization. So it can do both of these. It can do shared memory parallelism through threading, and it can do distributed memory parallelism through processors. So Python has a built-in threading library where it's, you import the threading library and then you can create threads. You can start and join them, so you can create a worker here, and then you can do some work, and then you can wait for that worker to finish at the end. So functionally, Python lets you do that. Unfortunately, the way Python is designed, you can create many threads, many workers inside your node, but you can't actually use any more than one at any one time because of something called the global interpreter lock, or the GIL, and that restricts parallelism. So Python lets you create mini workers, threads, but it doesn't let you exploit them to speed things up. Now, you may ask, why does Python let you do threads at all if you can only ever run one at once? And it's because it's possible to do some kinds of programming more efficiently with threads, things that you're waiting to happen in the background, such as waiting for a data to come from somewhere, or waiting for some interrupt from a user or something like that, and that's more efficiently programmed with a thread. So Python is restricted in that sense, so you can't easily create lots of workers to work in parallel using that method in Python and get any performance benefit. You can use the multiprocessing library, which lets you create effectively distributed memory workers, so that each individual worker is not sharing anything. And in that sense, you're not restricted by the GIL, so you can run them all in parallel. But you have to do this process of manually programming up the communication between them. And in Python, that's done with pipes or queues. In this multiprocessing library, it's done with pipes or queues, where you can define a pipe to send data backwards and forwards, and you can then manually send data between individual workers. The reality, of course, is that that's not really designed to do high performance parallel functionality. It's much more designed for what I call distributed or concurrent computing, because those communication mechanisms, the queues and the pipes, aren't particularly high performance and don't map well to high performance networks and things like that. So again, that's not something we would generally use for high performance parallelization of your code, but it is possible to do some stuff that way. Actually, where people get a lot of their Python parallelism from is what we'd call implicit parallelism, or what I would call implicit parallelism, where actually you call a library which itself has been parallelized, but it is not subject to some of the restrictions that Python is. And particularly NumPy and SciPy are examples of this. So the NumPy library generally builds on top of BLAS libraries, which are generally parallelized with a shared memory implementation to let you run up to 8 threads, 16 threads, 32 threads, and get speed up that way. So you can speed up your matrix vector operations, and SciPy can do exactly the same thing. So if you use an efficient and optimized NumPy and SciPy install, then you can get parallelism out of Python on a single node. And so you can run NumPy functionality to do large amounts of mathematical operations, and it will, if you want, automatically parallelize for you on the node. And that's one way you can get better performance out of an ARCHER2 node for a single serial Python program, is to use things like NumPy and SciPy. And then there's more complicated functionality on top of that. So you can do the same thing yourself, but rather than using NumPy or SciPy, you can write your own underlying C or Fortran or C++ parallel code and interface it. And if you're interested, if you look at our scientific Python course, we give a lot of details on how you interface the native code, and that can be one way as well. So you effectively use your Python as a language which is calling functionality from other languages. And then there is also an MPI for Pi, so there is a direct implementation of this message passing library as well, which you can use to do direct message passing inside the Python. So those are all parallel Python options. That's not the main one that I'm going to focus on now, though, because there are other libraries which give you that kind of functionality as well. And so one of those we're going to look at just now is called Dusk. And that's quite commonly used to parallelize your Python applications at a large scale without having to require you to do some of this reprogramming of things, which some of the other approaches require. So Dusk is actually what we would call a task parallelism library, and it's a library to do parallel computing in Python, where effectively it will break down your Python program into individual tasks and then run those on whatever resources it has available to it. So it has a sort of two-phase approach where it creates a task graph from your application, and then it runs that task graph on the resources you have. Now you have to program in a certain way to be able to unlock some of this functionality. But once you do, Dask will create this task graph and it will then run it for you. And it can run it on a single node in a shared memory like manner, or it can run it across as many nodes as you have access to. And it will deal with that for you. So as I say, what Dask fundamentally does is it builds a task graph, splits the work up, schedules that work on available compute resources, and then executes that work for you. But the nice thing about it is it can do it without you having to implement all that functionality yourself. So all you do is tell Dask what kind of things you want to do, and then it will take care of all the difficult parts of parallelizing and communicating and running things. So here's an example at the bottom here where we've created, and this is the kind of task graph that Dask creates, because this picture comes directly from Dask. You can get it to generate these kind of pictures for you from your workflows. And basically there's a bunch of functions or data types or variables which are feeding in to some operations, which feed into another function, which produces an output. And as this task graph shows, all these things on the bottom row can be done independently, and then the results of all of those need to be gathered together to do in a single place to do a sum and produce an output. And that's the kind of thing that Dask will be taking care of for you. Now, Dask has a number of different ways to enable this. It has a set of what he calls collections, or I would call data types, which provide built-in parallel functionality. But it also does give you some ways to program this directly as well, if what you're doing doesn't fit directly into these data types. Anyway, the fun ones that come out of the box with Dask are array, data frame, and bag, where array is really designed to map onto NumPy arrays. So effectively, it's meant to do very similar things to NumPy arrays, but in parallel for you. And particularly, it supports out-of-memory functionality, so it lets you create NumPy arrays or equivalents to NumPy arrays, which are bigger than you could fit into a memory of a single machine. Data frame is very similar, but it does that for effectively Panda data frame functionality. And so a Panda data frame is very much like a 2D table or a spreadsheet with a lot of functions built on top of that. And Dask provides its own version of a data frame to do parallelism across that. And then there's a more general data type called a bag, where you can do that with things that are not NumPy arrays or Panda data frames, but more general bits of data. And so NumPy, Dask gives you these data types, which lets you process these as if they were local data sets running a single Python process, but will use multiple compute resources to do that. You can also program Dask more directly, and there's sort of two ways to do that. Effectively, they're ways to build your own task graphs. So you don't use Dask's built-in data types, you use your own code, but you tell Dask what things are tasks and how they connect together. So effectively, you can create individual functions in your Python program or methods, and then link them together into a task graph, and then still get Dask to run it for you. So you can do that either using Dask.delay interface, which lets you construct the parallelization and Dask graph functionality, and then run it all once you've built your whole task graph. Or more recently, there's something called Dask Futures, which does a similar thing, but you don't have to build the whole task graph before you start running things. So you can actually do immediate task generation and you know, so you can partially evaluate your task graph whilst you're building it, which can be more efficient. And of course, as well as these functions, there are sort of data movement functions and coordination synchronization functionality if you're going to build these kind of things. Now, this is not what most people do. Most people are coming to Dask because they can map their Mpi array directly into it or their data frame directly into it. But it's just worth knowing that these more direct programming interfaces are available for you as well. And so what does this look like? Well, if we look at Dusk Arrays, we can see effectively it looks very like the NumPy array interface. So we import a Dusk array, we can create it with a certain size, and then the thing that's different about Dusk is you specify how to split that array up across workers. So if I was just running this in NumPy, it would be numpy.random, 10,000 by 10,000. Because this is Dask, I've got to specify this chunk element to say how much do I want to split this up across my workers, and how do I. Now, it's possible also to split things up in certain scenarios without specifying the chunking. You can get Dask to do it in certain circumstances to do the chunking automatically for you, but particularly for this Dusk array stuff, it's your responsibility to say, please split this up across a certain chunk size. And then what Dask does under the hood is for each chunk, it actually uses a NumPy array, and then it does the functionality to coordinate between them and run all the functionality on all the different ones and dispatch the data backwards and forwards. And so there's a whole bunch of functionality to do random arrays and what you'd expect from NumPy arrays. So there's all sorts you can do there. Actually, the documentation for Dask is pretty comprehensive, so you can go and look at the kind of different things you can do for a Dask array. You can do arbitrary NumPy arrays, so you can take the Dask, you can build your Dask array from an existing NumPy array, as long as that NumPy array supports a shape and number of dimensions and data type. And so there's more details on that, but you can just directly pull in a NumPy array into Dask. You can also pull it in from file. So Z-array files and NumPy binary files can be read directly in to Dask. You don't necessarily have to specify the chunks in that scenario. It will automatically do some chunking for you there. And then you can sort of concatenate and stack. So you can create Dask arrays from other Dask arrays. You can either concatenate a whole bunch of Dask arrays together, or you can stack Dask arrays into a multi-dimensional Dask functionality. We can also create a Dask array from a delayed function. So from this kind of functionality, we can build a Dask array out of it as well. So we can manually create a Dask array from a delayed function output. Now, I've not covered this actually properly yet, but one of the important things to remember about Dask, or to know about Dask, is that it's lazy. And lazy here doesn't mean imply anything bad. It just implies that it waits to do the work until the last possible minute. And from Dask's perspective, this is an optimization because it's going to wait for all the intermediate things to be ready, or for the whole task graph to be ready, so it can work out the most efficient way of doing things. Unless you do it with futures, where you're shipping the tasks immediately, then Dask will construct a task graph, but it will not actually run anything until you tell it to. So Dask arrays are lazy in the sense that you do this here, import Dask array as DA, x equals DA random.random size. At that point, you've created a task graph. You haven't actually created the array x. There is no data in x. There is nothing in x until you actually call a function on x called compute, which will then force x to be evaluated. And this is good because you can do x plus y equals z, and you can do give me the mean value of X. And Dask won't have to create all those intermediate results. It will just create the whole task graph of X plus Y plus Z and the creation of X and the mean of X, optimize that task graph and then run it. But it's something to bear in mind when you're doing Dask stuff, because if you don't ever put a compute in, you never actually get any results at the end. It just creates the graphs and then finishes, which is always slightly annoying. Dask Array, so remember this is the equivalent of Mpi Array, supports a range of Numpy-like functionality, but not quite everything. So you can do arithmetic and scalar mathematics on Dask arrays, reductions, so sums, means, standard deviations, those kind of things, indexing, slicing, transposing, array ordering, and it'll do all those things in parallel, and some linear algebra, SVDs, solves least squares, those kind of things. But it doesn't support everything that you can do in NumPy. So not all the linear algebra stuff is implemented. NumPy arrays have to have that shape and size and dimension actually properly defined, and NumPy lets you get away with some of that stuff that Dask won't. You can't do all sorts or necessarily to list, and iterating over Dask arrays is not generally efficient in the same way that iterating over NumPy arrays would be, because there are different ways you might want to do that. So there's a full API and more documentation on the Dask websites, but it's worth bearing some of those limitations in mind. Data frame is very similar, but of course, instead of being a NumPy array, it's a Pandas data frame. So the underlying data type is Panda data frame. The Dask data frame puts a bunch of those together. This time, you don't have to specify the chunk size necessarily. So the chunk size will easily be created for you by Dask, but you can specify a chunk size. So here we're reading one in from a CSV file like you would with a Pandas data frame, and you can see that we're not specifying here the size of it, but it is possible as part of read CSV function to specify the chunking or how you want to split that up across workers as well. And there's, just as you have in Pandas, there's lots of different functions to read your data frame in from files and data sources. We can create it from Dask arrays or from delayed objects or from bags, and from other objects as well. Now a data frame, again, just like the NumPy functionality, the Dask array functionality, supports most of Pandas, but not all of it. And so it will support independent operations such as element-wise, selections, aggregators, some group operations, and some group by stuff which requires data reordering. But it won't support everything. It doesn't support the full Pandas API, and it doesn't support. Well, there are some things which are expensive in it. So iterating over by row, just like in Dask array, iterating through them is slow on the data frame, just as it would be in a Pandas data frame. Setting new indexes on unsorted columns is expensive, and things like group by or join on unsorted columns that will actually do this setting the index are also going to be expensive. And then there's this general data type called a Dask bag, which is really meant to represent something like a list or a set, so sort of pretty standard Python data types mapping a big list or a big set into Dask. And so it can be an unordered collection of data with repeats. So repeats are fine and it doesn't have to be ordered. The important thing to know with Dask bag is once you create it, it's immutable, so you can't change it. You can create a new object from it, but you can't change it. And then it supports map, group by, filter, and fold operations, along with a number of other operations, which we outline in their documentation. And it's really designed for sort of parallelizing simple computations on unstructured or semi-structured data, so text files, log files, or user-defined Python objects. So if you have your own Python objects, your own data types in Python, then bag can be used to do a set of operations across those. Because of the Python, so the way Dask gets away with parallelism for the Dusk Array and the Dask data frame is that it can distribute each one of these chunks to a different compute node or a different worker on the same compute node. And then inside each one of these chunks, it can use the underlying functionality, so Pandas functionality or NumPy functionality to do the parallelism here. So NumPy parallelizing inside a single node here using shared memory threads, which it gets from its underlying data libraries like its BLAS libraries. And Pandas does a similar thing here. And so Dask is cheating in a way here, but it gets around the global interpreter lock parallelization problems that Python has by just calling a library which has already fixed that problem underneath it to give you that in-node parallelization functionality. Because bag itself is not using any underlying library, it's designed to map sort of standard Python data types. The Dask library has to implement the parallelism itself, so it uses multiprocessing, not threading, to do the parallelization on Dask bags, and that means the communication efficiency between bag elements is not as good as other kinds of parallelization strategies. So parallelizing across a bag, certain operations parallelized across a bag can be slower than, say, if you're doing a similar kind of thing with a Dusk array or a Dask data frame. And so what does bag let you do? Well, you can create bags from, say, sequences. So this can be from a list or a set or a tuple, from URLs, from text, from data frames. And then you can do things like accumulate, split, count, max, min, sum, and you can create sort of, there can be operators. You can do these different reductions with different operators. And so those are the kind of operations you can do on a bag. Here's an example where we would do you could go through and you could get a Dask bag and then filter on a function. So you can write your own functions to do operations on a disparate set of data. Here we've actually got data that's the same, it's all numbers in a range, but you can have a bag with a disparate set of data, write a function to do something on that, and then apply that across parallel workers by using Dask. And then there are, some things that you can also do. There's a thing called a fold by, which combines a reduction and a group by, which can do much more efficient sort of parallel split, apply, combine tasks. And that the fold by is designed to get around this group by thing being quite slow, and group by was quite slow in other implementations as well. So it tries to get around that kind of restriction. Now, having said all that, if you can get away with an array or a data frame instead of a bag, then you're going to have higher performance. The data frames and the bags are generally, data frames and the arrays are implemented more efficiently than bags. So the bag is something you need to use if you can't map your data to any other data types that will easily go into a data frame or an array. And then, as I said, and most people won't necessarily have to go to this level, but it's worth knowing that it's there, you can use Dask delayed or Dask futures to write your own task graph, where you create a set of functions and then run them on data in parallel. And so there's an example here. I create an increment function, a double function, and an add function. I create this is my Python program down here. I iterate over some data, and for each one, I do some work on the data, and then add it to an output, and I keep going on here. And this is all done in serial, there's no parallelization here, but you can see that for each iteration on each element of the data is done independently, right? So I could actually do the work on 1, 2, 3, 4, and 5 all at once if I can do it in parallel. And there are, you know, there's different ways of doing this in Dask, but you can do that. So one way is just to take exactly that program and then just put this function dask.delayed and call each of my user-defined functions here, inc double add, call each one of my functions as a delay task. That will build the task graph for me here. I do the sum as a function here, and then I call this total compute at the bottom, and that calculates the task graph, and that will parallelize it for me. And it should do, depending on how many workers I have, it should do these 15, these three function calls over 5 elements all at once, and then it should do this sum task at the end. But of course, it can't do this sum task in parallel until all the rest of these are finished. You can also, instead of putting these function calls in everywhere, because of course you've got a big code base, you've got to put everything in as a delayed function like this. That's maybe quite a lot of work. You can actually use code annotation, so some marking up of the code using this dask.delayed decorator just on the functions themselves, right? So if you want them all to be delayed functions, then all you need to do is dask delayed the functions. We are going to delay this sum at the bottom here as well, because that's not something we've defined here, and then run the compute on it, and that will do exactly the same thing. So these two, this example here and this example here, should be functional equivalent. And so you can also do the same thing with the futures thing, which, as I say, is a bit of a newer interface for Dask, but does a similar thing, but lets you run some of the stuff whilst you're building the task graph. And in that mode, we actually use this function. We create a client which runs things, and then we submit the function with the data it's going to run on, and that will start it running in parallel as soon as we tell it to. And then at the end, we can sort of wait. We can wait for the result to come out from this functionality and then use it elsewhere. So there's also this futures way of parallelizing as well. Now, again, there's a lot of detail here. You don't expect you to have to remember or even necessarily fully comprehend all of this stuff up front. Just trying to give you a broad overview of what Dask supports. As I say, I imagine 80% of people can get away with just using, particularly in data science, Dusk arrays, Dask data frames, and nothing else. But if you run into limitations there, then there is the scope to do things like bags, delayed in future, to do more complicated things manually yourself. Now we're going to move on here now to then talk about, so this is sort of abstract, this is how you program Dask. But of course, the other part of it is how you run Dask on the system. So how do you map to workers, how do you map to cores, how do you map to nodes, and what do you do specifically on ARCHER2? And so that's what I'm going to cover in the next few slides. But if there's any questions at this point, just shout at me, or drop a message in the chat, or stick your hand up, because things may have occurred to you whilst we're going through here. Otherwise, I'll plow on. Cool, so we shall keep going. So how does Dask actually do its parallelization? Well, now there are different parts of Dask that can be used, and in fact, there's a core Dask library, and then there are sort of extensions to the Dask library, and that does that. Now, the core Dask library, let's consider the core Dask library works inside a single compute node, and so this can be, how do you take some tasks and run it on one compute load in parallel from Python. Generally, Dask, unless you're running a bag, generally Dask will default to threaded parallelization, so this shared memory parallelization model in a single node, and it will try and use all the available cores in that node. It'll look up how many cores are available. So on ARCHER2 compute nodes, that'll be 128. It uses threads by default because that's generally a quicker, more efficient way of doing this kind of parallelizations for something like Dask. It's easy to share data between workers. It's easy to parallelize. The process, the multiprocessing way that the bag does it is heavier weight, but it gets around some of the problems that other bits of parallelization can have. So by default, a lot of the Dask stuff uses threads. It is also possible for you to change what Dask does, though. So you can set some configuration for Dask, like the scheduler that it uses. So here we've got this import dask.config.set scheduler equals threads. This is sort of generally what's done by default. But you can also do dask.config set scheduler equals process, and that can get you, if you're doing some work inside Dask, it may make more sense depending on how you're launching your Dask tasks. This is, again, all inside a single node. But there is something called dask.distributed, so which is an extension to Dask, which lets you submit jobs to multiple nodes and run parallel jobs across many nodes in a system. And there we use this thing called a client. So we import the Dask distributed client. Again, by default, it has a default. It defaults to processes rather than threads. But we can specify, we can change that as well. So we can say client equals client, process equals false if you want to use threads instead. In general, for most of these things, you can just accept the defaults that come, but it's worth knowing that you have the ability to configure that. It's also worth noting that Dask distributed is not installed as part of the core Dask installed. And on ARCHER2, Dask is installed as part of Cray Python, but Dask distributed isn't, so you need to install that yourselves. But Dask distributed lets you do multi-node stuff, and it gives you some quite nice dashboards like this. This stuff on the right-hand side here has come directly out of Dask, and the distributed stuff lets you see the tasks as they're running, the schedules, and what's going on. So that's one of the nice things about Dask, is it gives you this sort of interface into what your program's actually doing, what's actually being run, how much data's been stored, and those kind of things. You can customize the amount of resources and scheduler used for different parts of the Dask thing, because it may be that you want Dask to have access to 10,000 cores, but some bits of it shouldn't use all 10,000 cores because that may be slower. And so you can do things like, for an individual compute step, you can set the specific scheduler you want to use, or you can do it as a context for a group of code. You can use a with Dask context and then put some code inside that. You can set it globally, as we've seen before, for the whole program. And you can also specify things like the number of workers to use. So by default, it'll try and use 128 on Archer, an Archer compute node, but you can manually set it to a smaller number. And as we know, if you're using threads, 128 is probably not likely to give you optimal performance on Archer, maybe 64, maybe 32. So you can specify a smaller thread pool when you configure your program. And you can do exactly the same thing with a distributed scheduler, the client we saw earlier, where you can specify the number of workers that it uses as well. When we look at that distributed scheduler, so when we're wanting to look at using more than one node inside a single Dask program, there are a number of ways to do it. In fact, Dask gives you interfaces to a number of different job schedulers. And there's also another library we can use called Dask Mpi, which just lets you run your Dask program as a standard MPI as a standard MPI program on a cluster as well. For ARCHER2, what we will probably, if you're only using a single node, you can use a local cluster. But for ARCHER2, we have Slurm integration. So what we end up using is a Slurm cluster, and then you can use that to submit to large numbers of parallel jobs or parallel workers on the whole system on ARCHER2. And I'll show exactly how we do that in a second. So the guiding principles of Dask is, and actually, in fact, they say this on their own website, if you don't need Dask, don't use it, right? So NumPy, Panda data frames, things like that are faster than Dask. If all you're doing, fits within a single worker, fits inside the memory of a single node, doesn't require large amounts of resources, then adding Dask on top of it will just be an overhead. Okay, so you can just use the lower level functionality and get away with it. Of course, Dask is important when you want to use more than a single node, when you want to process data that doesn't fit into the memory of a single node, and these kind of things. The chunking and granularity, so how you split your data up across workers, is important for performance. If you create, chunks that are too big, then you're not going to be able to use many workers. If you create chunks that are too small, then you're not going to be able to, your parallel overheads, the cost of splitting up all that work across lots of workers exceeds the performance benefits. So there's got to be a little bit of playing around to get your best chunk size, but something that's in the middle, not too big, not too small, fits within the memory of a single worker, but lets you use sufficient workers, needs a little bit of tuning, but that's important to get good performance out of Dask. And you should call compute as infrequently as possible, but as many times as you need. I know this is not very helpful advice, but what compute does is it forces the evaluation of a task graph. So it makes Dask do the work you've asked it to do. If you do that too often, then you may miss opportunities for Dask to optimize out some intermediate steps, and you may end up with calling lots of small bits of work many times. Right. Okay, so this is why you shouldn't have to call that compute until you really need to in your program. The caveat to that is that if you've got a very large program or lots of work to do and you don't call compute right till the end, Dask may run into problems because the task graph may get too big for it to properly handle. And so again, there's a little bit of experimentation there. For small programs, a single compute at the end is fine, but for other ones, you may have to do something more nuanced. If we're going to do large-scale parallelization, so that's using many workers across many nodes, it probably makes sense for some of those to be processors and some of those to be threads. So it probably makes sense to split up our data Dusk Array chunks into reasonably big chunks and then use the underlying NumPy functionality, for instance, to use 4 threads or 8 threads for that, rather than trying to do it all as processors or all as threads. And then there's a couple of other things that can improve performance for Dask. One is load data with Dask. So don't load data into NumPy and then load it into Dask. Don't load data into Pandas and then into Dask. Although you can do it, because Dask is set up to support these out-of-memory data accesses, it won't load all the data in at once. At the beginning, it will do it as required, and that can give you better performance. If you're going to have to write your data to files at some point, it's best to do that once you've cut the data down. So, for instance, if you're going to do a reduction, a group by, then a fold by, or something like that, don't write the data in its largest form. Write it in its smallest form if possible. Okay, so how do we use Dask on ARCHER2? Well, as I say, the basic Dask is already available as part of the CreaPython installation. That only brings you the threaded shared memory backend and a single node functionality. If you want more than that, then you need to install the distributed and the job queue functionality, and you can do it like this: export your Python user base, export your Python path, and then just use pip to install it. And then what we need to do is run so we need to run a scheduler that needs connections from the workers, so we need to submit from a compute node. So what does that mean? Well, we can put it inside our batch program like this, as a normal batch program, Python Dask program, and that will use a single node, and that will do sensible stuff as long as you get your process placement and binding correctly here. You can also do that as an interactive task, as we've seen before. But if you want to go to more than one node, then we need to, inside this is part of your Python program here, we need to set up a cluster, a Slurm cluster, and you can just copy this. In fact, we have this on the ARCHER2 website where you can copy it directly from there. You specify things like your project, your wall time, your Python user base, and in here we're specifying I want, this is the size of an individual Dask job, so 128 cores, 128 processors. That's a single node. And then down here you say, you can specify in the cluster, you can say actually I want to submit 2 jobs, so that's 2 single node jobs. Then you create your Dusk Array and you compute it, and then this will, when you call compute here, it will submit the jobs, it will communicate with them, and it will create the data movement and calculation from there. So at the end you'll be using 3 nodes: your main controller node, which is running this program here, and then that will itself launch 2 other jobs to do the actual Dusk Array functionality itself. And that means you can scale your Dask tasks from a single node on ARCHER2 all the way up to 5,000 nodes on ARCHER2 if you really wanted to. Of course, you'd have to slightly change the QoS and the partitions and stuff like that. The Q and to Q here means partition and QoS here. But other than that, that gives you the access to the sort of full resources on a system like ARCHER2. So Dask, it has this functionality where it will take your job, your Python code, in various forms and parallelize it for you up to a certain, up to whatever point you ask it to. It has the functionality to build these task graphs and run them for you. Now, it's unlikely ever to be quite as efficient as if you manually wrote all this parallelism yourself and you manually wrote it in an efficient manner. Because it has some overhead, it has to create the task graph, it has to dispatch the tasks, it has to evaluate the tasks, it has to pull the data back. But what Dask is really aimed at, of course, is productivity. So it's designed to be easy to parallelize, so you don't have to do that parallelization work, and it just does it for you. And so there's a big win in terms of development time and user time in getting that parallel functionality up and running. So if you are trying to do a data analysis on something like a Mpi array or a data frame, which is going too slowly and much too big, you can't fit it in a single node, then Dask is a great place to start looking at, okay, how can I use this to actually, does it support all the functions I need? Can I get my job to run much quicker in this way? And in that way, you should be able to bring a standard data science workflow to ARCHER2 and parallelize it across the resources, and get your results back from that. Plus, it gives you some quite nice shiny things like these dashboards and stuff like that. Now, it's a little bit more complicated if you want to get the dashboards up and running, because you need to do some port forwarding and SSH forwarding to connect your browser to the Dask on the system. But it's possible. It's not terrible to do. We don't go through that level of detail here in this tutorial, but it's something you definitely can do and run your own Dask controllers and manage your data workflows in that way. Any questions? Well, I've somehow managed to stick to time, which is nice to see. It does mean that we can now go and have a look at another exercise. So let me just share the exercise screens again. If you're still didn't quite get to, haven't quite got round to doing the container stuff, and you feel free to have a look at that exercise 3. Otherwise, you can look at exercise 4, which is to do some of the things that I've outlined in the lecture, but yourself on ARCHER2, and looking at how that sort of functionality works for you, what kind of things you can do. So, can you do a Dask data array? Can you do a data frame? Can you write your own delay stuff? And then down here, there's a Mandelbrot set and a Pi calculation, which you can parallelize yourself using Dask array functionality. And then what we down here, we'd want to use a Dask futures functionality to do that yourself. So go and have a look at that. We've got notionally on the timetable, we've got half an hour for this practical until 3:30. Then we'll take a break until 4 o'clock, and then we'll come back and talk about R at 4 o'clock. And as always, any questions in the meantime, let me or Eleanor know. Any problems on ARCHER2, it would be good to hear about them. And any mistakes in the slides or the practicals, let me know as well. Yeah, so that's a good question, Dave. Yes, absolutely. So Slurm cluster will submit a job, and Slurm cluster will then interact with that job when it starts. Yeah, so now I need to go back and look at why this stopped working. You used to be able to run the worker on the Archer login nodes and then get that to submit the jobs. Some of the network changes we had meant you need to submit that sort of main worker, which is doing the control of the Dask workflow, to the back end, and then it will submit its jobs to the queue. Now, the slight annoyance about that, of course, is that whilst your job submits its jobs to the queue, it'll have to sit waiting until they run. And so that can mean there's a bit of delay and a little bit of inefficiency. But unfortunately, that's the way it has to be at the moment. And at least that way, your main job, your coordinating job, which calls Slurm cluster, is running on the compute nodes. You're not going to have a problem with it crashing on the login nodes or something like that. But yes, that's exactly what it does. You run your main job already on the compute nodes, then you run Slurm cluster inside your main job, and that does that queues it up, that submits something to a batch system, and that also talks to the batch system to work out what's going on. So yes, put the Python program inside a batch script, submit that, and then you would get your program running, and then it would submit its jobs from inside there. Yeah, absolutely. So each of us Slurm cluster jobs. So each Slurm cluster you set up defines their QoS and partition, or what we call Q and QoS. Whether you can change those between submissions on the cluster, I've never tried actually, but there's no restrictions. If you submit into the standard queue or the long queue, and then want to submit Slurm tasks into the short queue, for instance, from inside that job, there's no restrictions on that at all. You can do exactly whatever you want from inside that. Whether you'd need a different Slurm cluster inside your Python program to submit different types of jobs, I haven't checked yet, but it should be easily, one way or the other, sortable. Okay, everybody, we're going to get started with the last lecture in a second. So we're going to move on to R, beyond, rather than Python and Dask. But it's still time to ask any questions about the Dask practicals or the Dask lecture material, the Python in general, on ARCHER2 before we get going. Okay, so we've heard about Python and Dask being a common way, and not the only way, of course, but a common toolkit or framework that people use to parallelize Python applications on systems like ARCHER2. And so we've been through a little bit of the information about how you would do that on ARCHER2 and how you do that in Dask in general. And then what we will do here now is do a similar thing for R. So look at how we would use R on ARCHER2. And we've already looked this morning a bit about how you would install new packages in R on ARCHER2. But there are, just like the Python stuff, mostly this is specifying where the install location should be, making sure you're using the system installed version of R, and there are a couple of versions. But of course, as with Python, R will do some parallelization locally with threads for some functionality, but not for everything. And if you want to go beyond a single node, then we need to use some extra functionality to enable that. And just like Dask for Python, there are a number of different ways we can do parallel multi-node R calculations. Now, as I said with Python, as I said earlier, we're not here going to give an exhaustive list or particularly suggest exactly which ones you could use or should use. We just picked some which are commonly used to do parallel stuff on R, and some that are pretty easy to set up and run on ARCHER2. That doesn't mean that if you use other ways of parallelizing R elsewhere, it couldn't work on ARCHER2. There's nothing to stop you trying it. And then if you've got questions or issues, coming in and speaking to someone like me or speaking to the help desk to sort that out. But these are ones that we've tested and used ourselves. And one of the challenges with R is there are a lot of different ways of doing things, a lot of different ways of doing similar things. That's one of the benefits of the R ecosystem, is there's lots of user developed packages which you can install and iterate, and some of those over time have become part of core R, and others have continued as separate lives. So we'll look at some of that and see what that looks like. Again, it could be that we don't cover things that are key to your work or your research or things that you're trying to do. We can't cover everything here, but if you have specific questions that come up, what about this package X or package Y, or how would I do this, then just let me know as we're going on. We notionally have an hour to do this, and then half an hour practical at the end, very much like the Python practical, where you take the R, you install some packages yourself, and then try running some things in parallel. Typically, this lecture doesn't take me an hour anyway, so we have a bit of time left at the end for completing the practicals, discussions, or finishing early if that's what you need as well. Okay, so there's, just like with Python and with other kinds of programming languages and programming approaches, there are different motivations for looking for parallel functionality. As we've said, basic R functionality should just work out of the box on ARCHER2. You may have to install some packages, but it should just work. If it doesn't, let us know. But just like with any sort of data analysis or computational simulation, there are situations where you need to look at parallelizing things. Either an individual program takes too long to finish, so my computational work takes too long, my program takes too long, and that's commonly where we see people come into us for parallelizing their programs with MPI and OpenMP. You know, it's not uncommon for people to come along and, well, I've written this simulation application and it's producing correct results, but it takes a month to complete. Can we speed that up? Of course, for data analytics stuff, it could often be we've got too much data to process. So my program is quick enough, but I've got too much data to get through, too many files, too many data sets. So doing them one after another serially is just too slow. And as we've seen today, there are ways we can do that with job arrays, which means we can take the same serial program, which hasn't been parallelized, and run it pretty quickly across large numbers of resources on ARCHER2. And then, of course, my data is too large. So I've got a very big data set. I can't fit it into memory on a single node. And that was one of the key reasons of using something like Dask as well in the Python example, that it supports this out-of-memory data stores where you can have more data than there is memory available, and it only loads up bits that are needed at a time and keeps the rest of it on the storage on disk, and that way you can fit everything into memory and still do your calculations. Now, if you've reached that point with R, then of course, as I said, there's lots of different options and approaches for parallelizing R and for addressing some of these requirements. There's a good web page on the our website called High Performance Computing, which has a list of lots of different packages and approaches for doing parallelism. And so there's implicit parallelism and explicit parallelism. Implicit parallelism here are packages where it's building on something underneath, which is giving you some parallelism. So just like we saw for NumPy, or we discussed for NumPy or for Pandas in Python, there are a bunch of things in R which are automatically parallelized for you because they build on underlying mathematical libraries which themselves are parallelized. And then there are packages or approaches which let you explicitly do the parallelism. So there's an RMPI, and that lets you write your own parallel program in R. There are things that look like a bit like Dask in the sense that they give you batch system integration, distributed computing integration, and hardware resources. And in fact, because R's been around a while and some of this stuff has been around a while, there's things that plug into grid computing and those kind of things. You can interface directly down to native code, just like you can do in Python, and we didn't cover it particularly in the Python lecture in much detail, but there, just as you can in Python, you can in R, you can call down to code you've already parallelized in another language and just use R to call that. And then there's a bunch of packages, and the same is true of Python, which deal with this sort of big memory. I need large amounts of data that doesn't fit in the memory of a node. How do I do that? So in Python, there's something called X array or Z arrays, which allow you to do that. And that's what some of what Dask is built on top of. In R, you can do the same kind of things. So there's so we can look at shared memory parallelism, so things within a single node parallelizing up to 128 cores. We can also look at the distributed memory parallelism to go across multiple nodes. In R, there's sort of things which you could class as trivially parallel. So can I apply the same function or the same operation to lots of data independently? And there we can use these apply functions, lapply, sapply, papply, which are built into the core Python, core R language. or the map function, which does a similar kind of thing. Python gives us, or at least parts of Python, I keep saying Python, sorry, R gives us potentially loop parallelism as well. So there's a for each, which lets you iterate, split up iterations of loops. Again, the iterations of a loop need to be independent, but like if you're doing OpenMP programming and shared memory programming, and distribute that across workers. And similarly, there's a package called RDSM, which allows you to do similar kinds of loop distribution and threaded programming. And then in the parallel memory distribution, the distributed memory parallelism, then there are packages like Parallel Snow, RMPI, and these all have some mechanisms for communicating across nodes, distributing work across nodes, and gathering data, exchanging data, these kind of things. Then there are sort of packages like PBDR, which give you a set of functions which have been parallelized across nodes, and the for each, which you can use for loop parallelism on a single node. There are packages or extensions which let you also distribute those across multiple nodes. And this is, as I say, not meant to be an exhaustive list, but just to give you a sort of flavor. We can do things at the okay, I want to do the same thing across multiple different input data sets at the same time. Can I do that inside the core R language? Yes, I can. Okay, I've got a large loop which does lots of work. Can I split that up inside R using functionality it provides? Yes, I can. And can I move to these sort of more complicated distributed memory things as well inside R? And yes, I can. As I've already mentioned, R has some built-in parallelism because some of the functionality inside it builds on top of BLAS libraries and underlying maths libraries, which already have shared memory parallelism built into them there. So something like matrix multiplication, here C equals A times B. If your R has been installed in a correct way to use an underlying library, which like the Cray version of R has been on ARCHER2, then this one here will actually by default, I think, try and parallelize this A times B, or matrix multiplication of A and B, across 128 threads, if you call it like that. That's because it's calling down to the underlying maths libraries, it's calling the functions to do the matrix vector calculations from there, and it will give the parallelism that way. Now, of course, you're not controlling this particularly, it's just coming out of the core R language and it's just doing it for you. And not all of this is parallelized. So creating the two matrices is not parallelized because that's not a function which is done in the underlying BLAS libraries. But this function here is mapped down to that, so that will do that functionality for you. Likewise, some of the libraries you can import, particularly data.table, when you import it, can use we'll try and use multiple workers to do some of this stuff. And you can see this as something like Pandas data frames inside Python is doing a similar kind of thing. Now, by default on ARCHER2, as I say, on a compute node, it's going to look for all the workers it has available and try and use them all, 128. You can control that. So as I've said earlier in today, other points, using all 128 workers as threads is often not as efficient on a system like ARCHER2 because you're splitting it up across two processors, etc., etc. So you can control the number of threads that are used. And the easiest way of doing this, because all these underlying functionalities generally build on top of OpenMP parallelization, is to set this environment variable OMP_num_threads. Okay, so if I said export OMP num threads equals 2, then when I call import this library.data table, you'll see that actually instead of saying, oh, I'm using 128 threads, I'm using 2 threads here. And likewise, this functionality here, when it goes off and runs, instead of using 128 threads to do it, it's going to try and use 2 threads. So you have some control of this built-in parallelism. You can control the scale that it works at. And if that's the kind of underlying functions you're using a lot of, then you may not have to go to any of these more explicit levels of parallelism. And it may make sense to you, it probably does make sense to you, play around a little bit with these, controlling the number of workers you give to R to do this kind of stuff. And so instead of letting it use 128 workers on a single compute node, try 16 workers and see if that gives you the same performance or better performance. You can actually get better performance with a smaller number of workers. That's fine. And then, of course, you could then put multiple jobs on the same node. If you're each using 16 workers, then you could utilize all the resources on the node from doing that. As I say, Python also provides this idea of for doing trivial parallelism, or what we call task farms, or embarrassingly parallel farms, and very actually sort of slightly different flavors within R for doing this. There's what I would call trivial parallelism, where effectively what we're doing is executing the same code independently on different data sets or different initial conditions. And this is exactly what we could have done in Slurm using an array job. So we don't have to do this inside R. We could do this in inside Slurm itself, or we can combine a Slurm array job with an R job to do something like this. So here's an example where in R we're reading in command line arguments, and we're taking the argument that's passed to R to set a seed for a random number generator. We're reading in a data set, and then we run a k-means simulation or k-means analysis on that data set and producing the result. And then if we're inside our batch script, we call R script k-means trivial, which is what is the name of this program here, and we pass in a number, then it will use that number to specify a different seed for the random number generator, and that will let us do a k-means exploration across a range of initial conditions to get us varying statistical analysis of this data set. And of course, if we couple this up with an array job, then each array element that runs through Slurm gets a different number here, that sets a different seed, and then we're sampling our data sets. Now, of course, you may want to make sure that your random number generators are doing something sensible for you here, but if you're using random number generators to do statistical analysis, then you should do that anyway. This is very trivial parallelism in the sense that it requires you to do some manual processing of the data at the end. So you're going to get lots of different output files, and then you're going to have to do some work at the end to bring all that back together. But that would let you at least do some what I would call trivial parallelism. There's also similar kind of stuff, but done inside R rather than done from a Slurm array job, where inside R you split your data up, you apply a function to it, and then you combine the results at the end. So here we're looking more at using the parallel functionality that comes inside of R. We're using lapply, and that will apply this function I've defined, which again is just doing a k-means onto this data set, and then that will run that in parallel on a single node for me. So I read my data in. This is like the serial version of it here at the top. Read my data in, run the k-means on that data, print the result. Here instead, I read my data in, define what k-means I want to run on, and then say I want to do 4 blocks of 25 instead of doing one block of 100, I want to do 4 blocks of 25. Call that 4 times, and then at the end, I pull the data back from this result. So I use a function called sapply to concatenate the results together to get my data back together. And that sort of is not this trivial approach where I'm going to actually get 4 output values here, 4 output files, and at the end I'm going to have to manually process them outside R. Here I'm going to create 4 functions, run them all separately, but process the data within R to get my final results. So it's all within that single program, and then I could submit that as a single job using 4 cores on a single compute node. And then it's some of the functionality, will produce. So depending on what you're doing, the lapply functionality here actually produces you sort of a list of lists of answers. So here we're using lapply, and that gives us a list of lists, and then it is possible then to take that data and combine it into a single list or into a single vector. So unpack that result and concatenate it together into a single list. So it's not without challenges in sort of handling the data and processing the data, doing this parallelism, because it depends exactly what you're doing, depends exactly what parallel functions you're using here, but it is possible that you need to do a little bit of post-processing for your data once you've collected it, because each element has returned a list, and all of those have been concatenated into 2-dimensional lists, and what actually we want to do is turn it into a single vector. So we can use functions like do, call, combine, and put those things back together again. Now there are a bunch of other apply functions. So that's lapply. There's actually, I think, 4 of them, depending on what kind of data set you're parallelizing over. I think this is list apply, but there's also vector apply and set apply, and they all vary by the initial letter, but they do a similar kind of thing. And then there are extensions to this. So there's multi-core apply, MC apply, which lets you parallelize across processes rather than threads on ARCHER2. So here we now need to import this parallel library, and then we can just use MC apply as we had before and do exactly the same thing. And there we can again control the amount of parallelism we have. So we, instead of using OpenMP num threads, we use MC cores as an environment variable. I think by default on ARCHER2 it defaults to 2 processes, but you can change that when you run your job, and you can also specify that within the function call itself. So you can say, actually, I want to use 16 cores for this function call and 8 cores for that one, and those kind of things. And MC apply has you may ask why, when lapply does this and it does it automatically, why would I want to go to something like MC apply? Because we're still inside a single node. Why would I want to move from threads to processes? But MC apply does give you a bit more control over things like scheduling of the work and load balancing across workers and things like that. So, if each one of these function calls takes the same amount of time, then none of this matters. But a lot of the time in parallel processing and actually in statistical analysis or those kind of things, one call to k-means might take a minute with a certain data, with a certain set of parameters, and another call to k-means may take 10 seconds. And if you just split those up into even blocks across all your workers, you could have some workers finishing before other workers, and there we don't get what we would call a nicely load balanced configuration, and that's less efficient than we'd like, because we can have some resources sitting empty whilst others are still running. And so MC apply gives us functionality to look at some of those kind of things. So we can sort of do what we call pre-scheduling, turn off pre-scheduling. So actually give out work when people have finished it. Don't give it all out at the front and things like that. And if you've ever done any OpenMP programming, you'll have seen various ways to do that with threads as well in OpenMP. So you can do sort of dynamic task scheduling, and that can be beneficial to improve the performance of some of your applications if you're using this approach. There is also functionality beyond that. So there's MC apply, but there's also MC parallel. And so MC parallel lets you split up data across workers and then apply functions on those workers. So that lets you go, again, at a slightly higher level, lets you start to distribute your work and then distribute your data across workers and then distribute the work to those workers. So there's an example here where we've reading the data set. It's got it's certain size data set, and then we do some work on that and split it up in parallel to create a set of results. And we do the same across another piece of work, and then we can use this thing called MC collect, which goes and gathers the combined results of the results that have been calculated from our workers and pulls it back to our main process to get our data. So the parallel library has functionality to do both trivial parallelism applications, but also a bit more complex stuff on top of that. And then there's also a for each library. So here we're looking at, instead of applying a function, necessarily a function to lots of independent bits of data, we could be looking at having a loop where we want to split up the iterations of that loop across workers. Now, in this example here, it's exactly the same as if we'd written a function across lots of data. This is our same example from before, but we have a do loop, and that do loops over 4 blocks of 25, and we then do instead of doing an L apply, we're doing a for each do loop, and then we want to collect the data back together to get our final result. So of course, in this example, there's nothing really to separate the two particularly. We could have done it as a set of calls of a function, or we could do it as over a loop. But really what we're looking at here is, okay, you've got a program, you've got lots of loops in it. How do you parallelize that? Well, you could turn the loop into a function and then do lots of function calls, but that's probably counterintuitive for the way your program's structured. So instead, we can turn it into a for each loop. And likewise, if you've got a program where you've got lots of discrete functions and you want to call them on separate bits of data, then we could use the lapply, MC apply kind of approach. The nice thing about for each is it lets us do splitting up our data across workers, so we can combine it with the do MC library, so do multicore library, to bring in this do parallel function here. So we have a for each. Instead of having do, we've now got do parallel, and we've set it up to use 4 workers. So we've said create 4 workers, run this in parallel on those 4 workers, and then everything else stays exactly the same, and the library just handles that for us. And the nice thing about that is we can also do similar things so it's possible to register other for each handlers to do parallel across larger things. So do multi-core will stay inside a single node, but we can use other libraries to go beyond that, to go to multiple nodes, and potentially look at the batch system and submitting jobs into a batch system as well. And then likewise, the SMO library has something called parallel lapply. And so again, we can see here what actually we're doing is we're using the same functionality as lapply as we had before, but instead of calling lapply, we call parallel lapply. and we can create a cluster now using Snow from MPI processors, and then it will distribute the work across that cluster we create. So we're now starting to get to a functionality where you can use more than a single node, where you can parallelize up over many nodes. Now Snow by default is built on top of MPI, so it has this functionality to interface with R running as an MPI job, as a distributed memory job, and it just picks up the workers that have been created there already. And so this here assumes you've run R in parallel using an MPI job launcher to start it up, and then it can pull that kind of functionality in here. And likewise, there's the do Snow library, which is a very similar thing, but instead of doing lapply, it's parallelizing a do loop. So it's parallelizing do into do par. So here we've got the thing that looked exactly like our do par, which we were using with our do MC to parallelize that for each across multi-cores in a node. We can now parallelize across multiple MPI processes across a set of nodes. And so all of these do very, very similar things, but it depends on what scale of parallelism you're going to need, what scale of computational resources you're going to use, and exactly how your code is structured as to how you apply that to get parallelism for your particular example. And so we've sort of gone from pretty basic inside a single node up to going across multiple nodes, either in applying functions to data sets or splitting up loops across workers that we have. And now, as I say, that's not an exhaustive list. There are other ways of parallelizing in R, but that's a good place to start if you've got an existing R program and you want to speed parts of it up. Snow, the thing that we've already seen coming in here, which implements some of this stuff on top of MPI, the message passing distributed memory parallelization library, lets you also do this interfacing with MPI clusters, so we can actually run individual functions across a parallel cluster. So before, in the past, in the previous examples, should I say, it was creating a cluster and then it was using a parallel R apply or for each to do that parallelization automatically for you. But you can, using something like Snow, do a bit more parallelization yourself by defining a function and then calling it manually across that MPI cluster that's been defined across that set of workers, and getting data backwards and forwards from that. So there's a bit more control there if you want to move a little bit beyond the pure lapply for do par approach into doing these things a little bit more manually, because your program structure doesn't quite map onto some of these lower level features. If you want to try using R, Snow on R, and this is one of the examples we have in the exercise sheet, actually you need to install it in a little bit of a complicated way, because the default download and install thing fails on ARCHER2, so I had to make some changes to the source code and repackage that back up just to map onto the networks and the system we have on ARCHER2. So when we come to do that, obviously this stuff we've all talked about before, about how you build an optimized R environment on ARCHER2, so it picks up the compilers correctly. You're using the pre-installed R and the right compilers, and you need to specify that you want to install your new packages on the work file system, not the home file system. So you do something like this. Of course, for you, this is not going to be TA055, it'll be TA065, but that lets you do that. And then to install Snow, we first need to install RMPI, this package here, and so you can do that using this command here, and then you can then inside R install the Snow package, and that should work perfectly well. But let me know if you have any problems doing that. So that's all sort of examples of how you would use this kind of thing inside your application. Then beyond that, how do you then actually run it as a job on ARCHER2 on a compute node? Well, here's an example. All we need to do is set up our library, set up our paths, so R knows where to look for things we've already installed. And then Snow gives us this functionality, this wrapper script called Mpi Snow, which will launch an R job for you if you're running something like this here or this here or that there, those kind of functions. Or something like this example here. So, this is a little bit more of a complex Snow example of how we could write some parallel code in R. And we're doing a couple of things going on here. First thing we're doing actually is we're not manually specifying how many workers we want to use. We're picking up how many workers have been specified in the batch script by getting the environment variable slurm_mprox. And then we can use that to specify the number of workers we want to parallelize some of these things under. And then, in fact, that should be included in this get MPI cluster. But we set up an MPI cluster, we create a function, and then what we do is we export our data, which I've not showed you importing here, but we export our data across that cluster. So that splits up the data we want to run the function on across the cluster, and then we use this thing called cluster apply to take the functions we've written, apply it to the data we've split up across the function, and that will distribute the work to the workers and let them run. And then once we get the data back, we can then do some work on it and stop the cluster at the end. So this is the kind of thing you can start to write in R using some of the parallelization packages like Snow, which let us split up. In this example, it's trying to calculate what's the chances of two people sharing a birthday if you have a certain number of people in a room. And so that's doing some statistical analysis across there and producing a distribution from it, and then creating the result. So this is a theoretical probability. This is what it's calculated as the distribution, and then we compare the two together at the end. And of course, this one here we can calculate not in parallel. This one here has been calculated in parallel, and we can see how they come. And so that example there, you could run that exactly like this, where you just submit it on there inside a batch script and use this RMPI Snow thing to submit that. So here we're not actually launching in this example. Now there are which I've not included in here, but there are packages that let you submit Slurm jobs directly from your R script, and that is possible. In these examples that I've chosen to go with here, what they're doing is actually running it as if it was a distributed memory application. So I'm saying I want to run on 2 nodes, 128 workers per node. So it's going to run my R program on 256 workers. And then inside that, R will do the parallelism itself to use those 256 workers. Or in this example, I'm running a single node with 64 workers. It will call this functionality. It will know there are 64 workers, and it will go and distribute that across those 64 workers. Although actually here I've said nmax equals 50, so it's only ever going to go and use 50 of those workers across that because I've specified that. But you have that kind of control to do that distribution and parallelization of work yourself. And this means that you can split up different bits of work in different ways. You can potentially have different levels of parallelism going on in here. So, we have to remember that some of the function calls or the built-in R functionality will try and do parallelism themselves on the nodes as well. And we can get some interaction there. So if we're going to do some of our manual parallelism like this stuff, we probably want to disable some of the automatic parallelism that you get from R in things like the matrix multiplication, the data table stuff, just by specifying a small number of threads when we run the job. So setting OMP num threads equals 1 would mean that when we, exactly as we've got here, when we run this, each worker is only going to be trying using one core itself. It's not going to try and go up to 128 cores for its internal work. And then, because if you did that, you get sort of clashes between the internal workers and the ones you've set up themselves, and it impacts performance. But that's the sort of the kind of functionality that's pretty easy to implement and apply in R. Now, as I say, the entry-level stuff, the things that's worth starting off with are things like the trivial parallelism, where we're going to do some sort of splitting up that allows us to do L applies, MC applies, those kind of functionalities. Now, as we've seen here, it probably does mean a little bit of work to your application code if that's what you're going to do here, because we've moved from quite a simple code there to something where we have to split it up into a function, apply that function, then do some work on the results we get. And so that is a little bit more complicated than what we had here. But once we've done that work, it can be split up across any number of workers we want to do, we want to use, and that will produce potentially produce results in parallel for us, and also lets us apply different kinds of parallelism. So we can use single node parallelism, or we can use the multi-core parallelism, or we can go up to something like Snow and run the same thing across large numbers of processes inside the HPC system across multiple nodes. And so I think there's this sort of two-stage process for a lot of our parallelization, well, maybe a three-stage process. Can we look at seeing, are there inbuilt implicit parallelism things we can use, so the stuff that's already provided by R, and can we control those and make sure they're being used efficiently? Can we, are we using packages which have parallel stuff built into them, and some packages already automatically parallelize code for you, have already automatically parallelized their functionality? And then beyond that, can we, are we using lots of loops? If we're using lots of loops, can we turn it into a for each, where that for each we can turn into a do par and then parallelize that do par using a multi-core thing or a Snow thing? Or can we structure it in such a way that we can use an apply function, an L apply, an S apply, an MC apply, to split up those functions calls across multiple workers and get the data back? Now, and beyond that, you can do direct parallel programming in R, as we've seen, where we can specify exactly what we want to do, and there's an R MPI, and we can do direct MPI programming. But then, of course, you're starting to get the level of doing explicit parallel programming inside R. You may be getting to the point where you need to move away from R to a language where the parallel programming is more designed for that kind of functionality. Something like C++ for Fortran, these kind of things. And now, of course, it depends on what you're using from the core R language or from the libraries that R provides you, the tidyverse and things like that. Whether that will be a lot of work to move away from that. But once you're starting to get in direct parallel programming inside R, it's worth thinking, is this the right place to be doing this kind of program? And if it is, then there is the functionality there to do that. And then if not, can you look at another programming language which is more performant with parallel programming, and does it have the kind of libraries you may want to also exploit there. Okay, so as promised, we are slightly earlier than the 1 hour, so it's 45 minutes, got 15 minutes until 5. Are there any questions about the R parallelization stuff? If not, there's a second practical. Well, that's not a second practical. There's another practical to have a look at for R functionality. I'll just share it. It's practical 5, and we do similar kind of things as we did in the Python one, where we look at actually can we have a look at the implicit parallelism and see what happens? Can we control that? Can we use the data tables, and then can we do these apply, lapply, do that kind of functionality, and then go up to some of the more complicated distributed memory parallelism, which is covered in a bit more detail in the practical slide. So we can, there's some description of how you can do arbitrary parallelism across a number of nodes. It's not really where we are on ARCHER2 because we have this batch system, and we are going, we have the functionality already built into to parallelize easily inside the batch system, or to split up our work easily in the batch system. So rather than doing something like a sockets cluster, as you could do here, actually we can just use the Mpi functionality and exploit that there. And so there's explanations in how we do that kind of stuff on ARCHER2 and in R. So give it a try, and if you have any questions, come back and let me know. That's the last lecture there for today. That's where we're going to finish the talk material, and its practicals up till 5:30. I'll be around for questions if you have any. And the only other thing to remind you of, of course, is you'll get a questionnaire at the finish of the course to fill out about what was good about the course, what was bad about the course, all those kind of things. And so it's always great to get that feedback. It's always useful to get the feedback. So if you have the time when you get emailed that, if you could fill that out, that would be good. And just let me know if you have any questions.